Hello everyone, this is Mesut Özdağ. Welcome to another lecture in Python programming language. Please subscribe to my channel and like my videos for more content in Python programming. This is lecture 1, part 2. The previous section demonstrated how names can be used to identify existing objects and how literals and constructors can be used to create instances of built-in classes. This section describes Python's expressions and operators in different contexts of the built-in types. Existing values can be combined into larger expressions using a variety of special symbols and keywords known as operators. The semantics of an operator depends on the type of its operands. For example, when A and B are numbers, the syntax A plus B indicates addition, okay, the mathematical operation of addition. On the other hand, if A and B are strings, the operator plus sign indicates concatenation. Logical operators are used on conditional statements, either true or false. Python supports these operators for Boolean values such as AND, its logical AND, true if both the operands are true, the syntax is X and Y, the OR operator, logical OR, the output is true if either of the operands is true, the syntax is X or Y, NOT operator, it's logical NOT, the output is true if operand is false, and the syntax is not X. Logical AND operator returns true if both the operands are true, else it returns false. Here in this diagram, we are looking for the output of X and Y. If X is false, the output is going to return false. If X is true, we're going to look for Y. If Y is false, the output is false. If Y is true, the output is true. So we note that if the first expression evaluated to be false while using AND operator, then the further expressions are not evaluated. Here is an example for AND operator. We have three numbers here. A is equal to 10, B is 10, C is minus 10. So if A is greater than 0 and B is greater than 0, we're going to print two numbers are greater than 0. And we have another if statement here with else that we're going to cover this later, this structure. So the output of this program is going to be these two statements that is correct for the if statements. Two numbers are greater than 0, at least one number is not greater than 0. Logical OR operator returns true if either of the operands is true. Let's have a look at the diagram of OR operator. So we have X or Y is going to return true if X is true. If X is false, we check Y. If Y is false, the output is false. If Y is true, the output is going to be true. So we note that if the first expression evaluated to be true while using OR operator, then the further expressions are not evaluated. Here is an example for OR operator. We have three values here. A is 10, B is minus 10, C is 0, and we have if-else statements, two if-else statements. And the output of this program is going to be, depending on the if statement, if A is greater than 0 or B is greater than 0, then we're going to print this, else this statement. And the second condition that we have, and the output of this program is going to be either of the number is greater than 0. That's correct. No number is greater than 0. Based on this second if-else statement, that's correct. Logical NOT operator works with the single Boolean value. If the Boolean value is true, it returns false, and vice versa. Here is the diagram for NOT X operator. So if X is true, the output is false. If X is false, the output of NOT X is true. Here is an example for NOT operator. So we have A as 10, and if not A modulo 3 is equal 0 or A modulo 5 is equal 0. So if one of these conditions inside the parentheses is met, the condition is going to go to the body of else statement. So here the output of this program is going to be 10 is divisible by either 3 or 5, which is correct. Here are the comparison operators: less than or equal to, greater than or equal to, not equal to. These comparison operators compare two values and return a Boolean value, either true or false. These operators have expected behavior for numeric types, and they are defined lexicographically and case-sensitively for strings. An exception is raised if operands have incomparable types, as with 5 is less than hello. Another example, two strings are considered equivalent if they match character for character. Two sets are equivalent if they have the same contents, irrespective of order. Here are some examples for less than operator. We have values for x 10, y is equal 20, x is less than y. Let's see what it returns. That's true. So the less than operator compares two values and returns true if the value on the left is less than the value on the right. Otherwise, it returns false. We can also compare two strings. The expression apple is less than orange returns true because the letter A in apple is before the letter O in orange. Orange apple is going to be false. And let's have a look at greater than operator examples. So we have these numbers for x 30, y 40, and let's see if x is greater than y, it's going to return false. Y greater than x is going to return true. Kale, spinach, false. Spinach, kale, true. Here let's have a look at less than or equal to operator examples. We have x is equal to 10, y is 20, and let's check if x is less than or equal to y, which is true, and y is less than or equal to x, it's going to be false. 30 is less than or equal to 30, it's going to be true. For the greater than or equal to operator example, let's have these values. X is 30, y is 40, and let's check if x is greater than or equal to y, which is false. Y is greater than or equal to x is true, and 50 is greater than or equal to 50, it's going to be true. Let's have a look at some equal to operator examples. So this line is going to check if 20 is equal to 20, which is true. 20 is equal to 30, false. Apple is equal to apple, which is true. Apple, orange, which is going to be false. As you can see, we can use equal to operator for strings as well. For not equal to operator examples, we have 40 not equal to 40, that's false. 40 not equal to 50, which is true. Apple not equal to apple, that's false. Apple not equal orange, which is true. Here are the arithmetic operators in Python. For addition, subtraction, and multiplication, if both operands have type int, integer, then the result is going to be an integer. If one or both operands have type float, the result is going to be a float. Division float is also called true division. It divides the first operand by the second. Floor division is also called integer division. Again, divides the first operand by the second. True division is always of type float. Integer division is always integer, with the result truncated. We have the modulo operator here. Modulus returns the remainder when first operand is divided by the second. And we also have a power operator, returns first raised to power second. Here is an example for using arithmetic operators in Python. So we have addition, subtraction, multiplication, and so on. And if we want to print all these results of these operations, the output is given here. So I would like to give you some homework. When it comes to negative values, what do we do for some integer division and modulo operators? So let me give you some hints. Let's assume that variables n and m represent respectively the dividend and divisor, so that q is equal n integer division m. R is going to equal n modulo m. So when the divisor m is positive, we know that 0 is less than or equal to r, r is less than m. When the divisor is negative, we know that m is less than r, r is less than or equal to 0. Here we talk about bitwise operators. We have bitwise complement, bitwise AND, bitwise OR, bitwise XOR, shift bits left, shift bits right. Computers store all kinds of information as a stream of binary digits called bits. Whether you are working with text, images, or videos, they all boil down to ones and zeros. Python's bitwise operators let you manipulate those individual bits of data at the most granular level. You can use bitwise operators to implement algorithms such as compression, encryption, and error detection. Most of the bitwise operators are binary, which means that they expect two operands to work with, typically referred to as the left operand and the right operand. Bitwise NUTs or bitwise complement is the only unary bitwise operator since it expects just one operand. A notable feature of any positional system is its base, which represents the number of digits available. People naturally favor the base 10 numeral system, also known as the decimal system, because it plays nicely with counting on fingers. Computers, on the other hand, treat data as a bunch of numbers expressed in the base 2 numeral system, more commonly known as the binary system. Such numbers are composed of only two digits, 0 and 1, as in this example in this slide. Here is an example for bitwise AND. We have an expression A, let's say, is equal to this binary value here and 156 as a decimal value, and B is a binary value here and the decimal value 52. So bitwise AND has two bits turned on in the positions where both operands are ones. In all other places, at least one of the inputs has a 0 bit. Arithmetically, this is equivalent to a product of 2-bit values. We can calculate the bitwise AND of numbers A and B by multiplying their bits at every index I. Here is an example for bitwise OR. So again, we have the values A and B. We are going to apply bitwise OR. So for each corresponding pair of bits, it returns a 1 if at least one of them is switched on. Only a combination of two zeros gives a 0 in the final output. The arithmetic behind it is a combination of a sum and a product of the bit values. To calculate the bitwise OR of numbers A and B, we need to apply this formula here to their bits at every index I. Here is an example for bitwise XOR. The name XOR stands for exclusive OR, since it performs exclusive disjunction on the bit pairs. In other words, every bit pair must contain opposing bit values to produce a 1. So we have the same values for A and B. It's going to be 168 in decimal value when we apply XOR to AB. Here is an example for bitwise NOT. As we mentioned before, bitwise NOT expects just one argument, making it the only unary bitwise operator. The inverter bits are a complement to 1, which turns zeros into ones and ones into zeros. It can be expressed arithmetically as the subtraction of individual bit values from 1. So A, bitwise NOT A, is going to be 99 in decimal value. Here is an example for bitwise left shift. Bitwise left shift moves the bits of its first operand to the left by the number of places specified in its second operand. So it takes care of inserting enough 0 bits to fill the gap that arises on the right edge of the new bit pattern. So if we have this example, A, bitwise left shift by 1, we see that we are adding 1, 0 on the right edge, and 39 becomes 78 in decimal value. Shifting bits to the left corresponds to multiplying the number by a power of 2 with an exponent equal to the number of places shifted. Here is an example for bitwise right shift. The bitwise right shift operator is analogous to the left one, but instead of moving bits to the left, it pushes them to the right by the specified number of places. The rightmost bits get dropped. Having an odd number, such as 157 in decimal value, would produce a fraction. To get rid of it, the right shift operator automatically floors the result. It's virtually the same as a floor division by a power of 2. This slide shows some operators that we can use for built-in sequence types, string, tuple, list. So we have S square brackets J, meaning element at index J, we have another operator here that means slice, including indices, with start included, stop excluded. And we have another one here, slice including indices, start, incrementing by step until the stop. We have S plus T for concatenation of sequences. We have multiplication. We also have value in S. We have value not in S. The notation val in S can be used for any of the sequences to see if there is an element equivalent to val in the sequence. For strings, this syntax can be used to check for a single character or for a larger substring. Here we cover some sequence comparisons. Sequences define comparison operations based on lexicographic order, performing an element-by-element comparison until the first difference is found. In this example, we have a list that includes 5, 6, and 9, and we have another list, 5, 7, and we check if this is less than the second one, and that's true because of the entries, and at index 1, 6 is less than 7. Here we see some operators for sets. Key in S, key not in S. These are containment and non-containment checks. We have equivalent check, we have not equivalent check, we have subset check, we have proper subset, we have superset and proper superset. And this OR operator that we saw earlier means the union of S1 and S2. This AND operator is actually the intersection of S1 and S2. This subtraction operator, meaning the set of elements in S1 but not S2. And this is the set of elements in precisely one of S1 or S2. Let's have a look at a set union example. As a reminder, we know that the set union returns the set of all the elements of both the sets without duplicates. So the first set we have 1, 2, and 3 in curly braces. In a second set we have 3, 4, 5, and then if we want to apply union method to union method with first set to the first set with the second set, we're going to have 1, 2, 3, 4, 5. As we know that we have 3 in both sets, so it's not duplicate in the output. Or we can apply this syntax to get the same output. For a set intersection example, we have this first set as 1, 2, 3, 4, 5, 6, and second set as 4, 5, 6, 7, 8, 9. When we want to have the intersection of these two sets, we apply intersection to the first set with the second set with this syntax, and we're going to have this intersection set, which is 4, 5, and 6. Or we can use the AND operator with a first set with a second set and get the same result. As an example for the set difference, let's say we have the first set 1, 2, 3, 4, 5, 6, and the second set 4, 5, 6, 7, 8, 9. If we want to apply the difference operator to these two sets, we're going to have 1, 2, 3, since we want to return the set of all the elements in the first set that are not present in the second set. Or we can apply the subtraction operator to get the same result. This is an example for the set symmetric difference. So we have the same set here for the first set, and the second set is the same as before. And we want to apply symmetric difference method to the first set with the second set. And we're going to have 1, 2, 3, 7, 8, 9 as a returning set, because it's the set of all the elements that are either in the first set or the second set, but not in both. Or we can use this overhead operator to get the same result. Here are some examples for operations that we can use to modify sets. Here we have two sets, A and B, and we want to apply update method to A with the dot operation, and it takes B inside the parentheses. Basically, it's a union operation without duplicates. We have A and equal B, meaning the intersection operation, and it's the same as A is equal A and B. We have the difference operation that we can use the same syntax. So A minus equal. We have another set that includes 7, 8, 9. So the difference operation applies to these two sets, and we have 4, 5, 6. And the same as the symmetric difference operation example here. Here are some operators that we use for dictionaries. As we know, dictionaries have key-value pairs. So the key is going to give us the value associated with that given key. In order to remove key and its associated value from the dictionary, we use the del operation. And for the containment check, we do key in D. For the non-containment check, we do key not in D. We have equivalent check and also not equivalent check for the dictionaries as well. Here is the table for operator precedence. Operators in a category with higher precedence will be evaluated before those with lower precedence, unless the expression is otherwise parenthesized. Here, let's say multiplication and division has the higher precedence than the addition and subtraction, and also than some conditional statements.